So I'm going to talk about infinite order rationally sliced knots, and this is joint work with Seung-Young Kang, John Park, and Matt Staffordin. My notes as I'm writing should be syncing with Dropbox, which I just sent in the chat. Sometimes it doesn't sync, so I'm sorry if it doesn't work, but the notes as I write maybe will be available at that link. Great, okay, so like the theme of this workshop, I'm going to be talking about link homology and concordance. So I'll be talking about the knot concordance group. So as most people here are probably familiar, well, this consists of the set of knots in S3. We mod out by the set of slice knots. And then we look at the operation induced by connected sum. So remember that K is slice if K bounds a disk in the four ball. So think of S3 as the boundary of the four ball. So closely related is this following group. I'll denote it CQ. So again, this will be generated by knots in S3. And now we'll mod out by rationally sliced knots. And so what is a rationally sliced knot? Well, K is rationally sliced if K bounds a smooth, properly embedded disk in, well, instead of B4, now we'll relax it and we'll just say in a rational homology ball. All right, so there's an obvious map from C to CQ, right? This is a surjective map. They're generated by the same things, but you're modding out by more stuff. And so then, well, you can look at the kernel of this map, which I'll denote C sub QS for rationally slice. Right, so this is the subgroup of rationally sliced knots. So these are knots that bound in a rational homology ball. And so the goal of what I want to talk about today is sort of understanding this group of rationally sliced knots. And so the main theorem is the following. Which is that this subgroup of rationally sliced knots, well, it contains the infinite rank subgroup. And I can tell you what it's generated by. It's generated by some pretty simple knots. So it's generated by the 2n plus 1, comma 1 cables of the figure 8. So remember, the figure 8 is rationally sliced. So if I take a P1 cable of a rationally sliced knot, that's also going to be rationally sliced. So it's clear that these knots are rationally sliced. And so where is the work? Well, the work is showing that they're linearly independent. All right. And so how does this compare to what was previously known? Well, these are the first examples of elements of infinite order in this subgroup of rationally sliced knots. So all previously known examples, whose order that we knew were order 2. And in contrast to what happens in higher dimensions, so sort of the analogous statement is false in higher dimensions. I'll say more about what I mean by that. And what tools does the proof rely on? Well, the proof relies on a computation using bordered floor homology. So that's how we compute sort of the invariance for this family of knots. And then the proof of linear independence relies on involutive Hilbert homology. Okay, so the structure of the talk, well, first I'll sort of tell you about some background, what was known about the, and then I'll talk about the key ingredients in the proof. All right, so what was one of the earliest tools for studying the knot concordance group? One of the earliest tools was the algebraic concordance group. So this is defined by Levine in the 60s. So the algebraic concordance group, well, it consists, it's generated by Seifert forms. Right, so you take a Seifert surface for your knot, and then you look at the linking form on H1. And if you quotient out by metabolic forms, so remember a form is metabolic if it vanishes on a half-dimensional subspace. And you look at this set under the operation of direct sum. Well, this forms a group, and this is completely algebraically defined, and so you can show that this group is isomorphic to z infinity plus z mod 2 to the infinity plus z mod 4 to the infinity. Great. This z to the infinity you can see by taking the Levine-Tristram signatures of your Seifert form. So that's where the infinite order part comes from. Great, and so what you get is there's a surjective homomorphism from the concordance group onto the algebraic concordance group. It turns out that the kernel is non-trivial. This is due to Cassett and Gordon in the 70s. And in fact, you can use this algebraic concordance group to show the knot concordance group contains z to the infinity plus z mod 2 to the infinity as a subgroup. Sort of all known examples of things that sort of hit the z mod 4 actually come from infinite order, as far as we know. Okay, so this is what happens in the classical dimension. You could define everything in a higher dimension. Recall, well, you can define a higher dimensional concordance group. So this is going to be generated by S2n plus 1s embedded in S2n plus 3.
Jen, can I ask a question?
Yeah.
On the previous line, did you mean that sits inside the kernel?
Oh, this line. I'm just talking about the structure of the concordance. We know that the concordance group has a because this is a subgroup. That's right. Are there any other questions?
But it is known that also sits inside the kernel.
Yeah. Oh, yes. Yeah. Yeah. Here I'm just giving background on the concordance group. So, but yes, Matt is correct. But yeah, it's known. But so you can define the concordance group in higher dimensions. You can in even dimensions, it follows some work of Curvaire that it's trivial. So we'll focus on odd dimensions. And in fact, Levine in these higher dimensions, the concordance group is actually isomorphic to the algebraic concordance group. So this is for, I guess, n. All right. If you want to talk about rationally sliced knots, well, if K is rationally sliced, that follows from work of Cha and Co. that the living system signatures of K vanishes. And so then in particular, well, in higher dimensions, well, this implies that K is torsion because of this isomorphism here. This is torsion in the higher dimensional concordance group. So this is what I meant when I said that sort of the analogous statement about the main is false in higher dimensions, because in higher dimensions, if you're rationally sliced, then you're torsion in the concordance group. All right. Great. And so we know that the concordance group has elements of order 2. How can we build elements of order 2 in the concordance group? Well, recall that if K is negative amphichiral, that is, it's isotopic to the reverse of its mirror image, right? So K is negative amphichiral. If K equals minus K, minus K is the reverse of the mirror image. Well, any negative amphichiral knot, or more generally, any knot that's concordant to a negative amphichiral knot, we know it's going to be order 2 in the concordance group because it will be its own inverse. So if K is concordant to a negative amphichiral knot, this implies that K is order 2. Great, and so the converse is open. Okay. So what do I know about this subgroup of rationalists? For example, we know that the figure 8, well, generates a Z mod 2 subgroup of this subgroup of rationally sliced knots. Well, how do we know this? Well, the figure 8 knot is rationally sliced. This can be seen by work of Finterschel-Stern from the 80s. The figure 8 is not sliced. This can be seen from living homomorphism. And while the figure 8 is order 2, since it's negative amphichiral. And in fact, you can generalize this. So you can actually find a Z mod 2 to the infinity subgroup in this rationalist knot. So this is due to Cha. And the picture is just the following. So take this knot and put n twists here and minus n twists here. Notice that if n equals 1, well, this gives you the figure 8 knot. All right. So I've talked about negative amphichiral knots. I also talk about strongly negative amphichiral knots. So we say that K is strongly negative amphichiral. If there exists an orientation reversing involution phi that takes K to itself. And what does this have to do with being rationally sliced? Well, how we prove that K is concordant to a strongly negative amphichiral knot then K is rationally sliced. So let me sketch the proof of Kawauchi's result. Okay, so if K, suppose K is strong via an involution V. Well, then this induces a fixed point free involution on the zero surgery along K. Wait, so I'll call it phi tilde. All right, and so we can quotient by this action. So let Y, the zero surgery along K, quotiented by the action induced by phi. And let's take the twisted I bundle over Y. And observe that the boundary of this is exactly the zero surgery along K. Great. So what do we have? We have this four manifold, this twisted I bundle, whose boundary is zero surgery along K. And then what we can do, you can attach a two handle to get back to S3, attach handle to get back to X3. And then it's not hard to convince yourself that the co-core, the co-core gives you a disk whose boundary is K in this rational homology ball. That's a sketch of the proof. Great. So the point is that Kawauchi showed that if K is concordant to a strongly negative amphichiral knot, well then K is rationally sliced. And so a corollary of our main theorem is that the converse to Kawauchi's result is false. Right, because you give an infinite family of rationally sliced knots that are infinite order. So in particular, like they're not concordant to a negative amphichiral knot. Are there any questions so far? All right, so now I want to talk about the proof of the main theorem. So the proof of the theorem, it relies on bordered flow homology, which is due to Lipschitz, Thurston. The way we use bordered flow homology, we use the interpretation in terms of immersed curves, so it's due to Hanselman, Rasmussen, and Watts. And in particular, since we're considering cables of the figure eight, we use Hanselman Watson's description of cables in terms of immersed curves. So it's this bordered flow homology computation of the knot flow complex of these 2n+1 cables of the figure eight. And then we have to compute the involutive knot flow homology of these knots. An involutive knot flow homology is due to Hendricks and Manilescu, and then also we have to use the connect sum formula, which is due to Hendricks, Manilescu, and Zemke. So let me remember what I mean when I say CFK. So you can think of CFK as a finitely generated chain complex. We'll think of it as a finitely generated chain complex over the ring F adjoin UV. So U are two variables. F is the field of two elements. Great, and so the point is, well, if you have a doubly pointed Hager diagram for your knot, well, you should think about U is counting how many times you cross the base point W, and V is how many times you cross the base point Z. So maybe we have W here, Z here. And so if you're thinking of these things sort of pictorially, I like to think of the ring F adjoin UV sitting in the plane, and sort of the horizontal distance is going to measure the U powers, and the vertical distance, the height measures the V powers, and then sort of I think of it as sitting in the plane like this. Okay, and then well, associated to this Hager diagram, then you'd see that the boundary of B is going to contain A, and you cross the base point W. So you see an A here, and then this goes to, sorry, this should be a B. B, and this goes to UA. And then we also see a disk from B to C that crosses the base point Z. So this is going to give us, so saying the boundary of B is UA plus BC, and the boundary of A is 0, and the boundary of C. And so as shorthand, sometimes it's convenient to just sort of draw this as the following. This, like this little L-shaped doodad. Okay, right. So the homotopy type of this chain complex is a knot invariant. But if you're interested in studying concordance, well, you might want to understand, well, what part of this chain complex is a concordance invariant. So you can define something which we'll call CFK connected. And sort of like philosophically, you should think of this as the summand of CFK that supports the homology. So maybe supports like the homology after you invert U and V. Okay, and so sort of this is implicit in earlier work of myself, and also Zemke, and maybe the idea of calling it the connected complex, that was sort of first done by Matt Staffordin in the pin 2 setting for 3 manifolds. And then Kristen, Ty, and I did it with 3 manifolds. And then this is written down in the case of knots by Hugo Zhou. Great. So the point is that, well, CFK connected, this is a concordance invariant. So let's take a look at some examples. So for example, if you look at the connect sum of the trefoil with itself, if you want to sort of draw a picture of its complex, it looks like this. Great. And then the point is, well, the summand that supports this here is this sort of staircase piece right here. So CFK connected, well, it's the summand that supports this localized homology, and it's this part. So that part is a concordance invariant. And this is not. So maybe another example, if you look at the figure 8, well, it's not floor complex. Looks like a square in this single generator. And so, well, the part that supports this localized homology, well, that's just this single generator. This is what the connected complex looks like for this knot. If you were to look at something like the 2-1 cable or the 2-1 cable of the figure 8, well, it's not floor complex. Looks like you get these 2 rectangles, and then you get this single generator. So CFK connected is just this guy here. And then if you were to look at something like the 3-1 cable of the figure 8, that has 4 summands. It's not floor complex, so sort of 4 distinct summands. 2 longer rectangles. Then you get this sort of funny shaped piece here, and then a single generator. So CFK connected is just this guy right here. Okay, and so how can you make this more precise, right? So what's sort of like?
Can I ask a question, Jen? Sorry.
Yeah.
So in several of those contexts that you mentioned that sort of as context for connected, I mean that there's an involution. So I mean, but it sounds like what you're talking about is sort of the sort of stable equivalence class here. And is that actually CFK? Is that actually the connected complex with respect to the identity involution? The identity is kind of trivially an involution.
Right. Yeah. I'm gonna add the involution in a moment. I'm sort of setting things up without the involution first, and that's what these examples are illustrating, and then we'll sort of upgrade this to the involution. But
if but the identity is an involution, and so if I define connected homology with respect to the identity,
then you
just get this. Okay.
Yeah. Okay. And maybe you're unhappy that this is not very precise. So let me just give you the formal definition of one way you could define these things. Great. So you could define a local map F from the not floor complex of K1 to the not floor complex of K2. Great. So what is a local map? Well, it should be an F adjoint UV equivariant map, equivariant chain map. Such that it induces an isomorphism on this localized homology. Great, and what does this have to do with concordance? Well, the point is that K1 and K2 are concordant. Well, then there exists a local map between their not floor complexes. In fact, you get local maps in both directions because concordances sort of don't really have a direction. Okay, so that's what a local map is. And then we can define a self-local map. We'll call self-local equivalence. Is a local map from the not floor complex to itself. Okay. And then you can say that a local equivalence F is maximal if for all right, so F is a self-local equivalence. So self-local equivalence F is maximal if for all self-local equivalences G, the kernel of G is contained in the kernel of F. So self-local equivalence is maximal if it has like the biggest possible kernel self-local equivalences. And then one way to define this connected complex is just the image of any a maximal self-local equivalence, so it's the image of F where F is any maximal self-local equivalence. Yeah, and this sort of has a sort of different name. So as Matt mentioned, you could think about this as sort of the smallest representative of the stable equivalence class or the nu plus equivalence class. Okay. And notice in all of this setup, we haven't used an involution yet. So what do Kristen and Cyprian give us? Well, they give us involutive knot-flow homology, right? And so that's this endomorphism iota k from the knot-flow complex to itself. This is it's a skew equivariant. So just swaps the actions of U and V. And it has this nice formal property that it squares to be homotopic to this. Okay. And so what's sort of the very rough what iota k does? So the very rough philosophy is that iota k pairs up symmetric summands and then an unpaired summand might be intertwined with CFK connected by iota k. And then you can define the iota k connected complex. And so very roughly, well, this is going to look like the connected complex and then plus whatever summands got intertwined with it, iota k. And so then the point is that this complex here, this is a concordance invariant. And so that's the rough idea. So let me tell you the formal definition.
May I have a question?
Yeah.
May I have a question? So is it the same as if you define like CFK, the iota complex CFK, and then extend the definition of local equivalence for that you just wrote for involutive homology?
Yes. Yep. Yeah.
Okay.
So I'm going to give the formal definition, and basically it's just going to be identical to the formal definition above, but we're just going to put in the involution everywhere that it sort of makes sense to. Yeah. Great. So the formal definition. Great. So let me just take the old definition and copy it, and then just add in some words. Okay, so let's make this an iota k local map. Great, so well, this map should be, this map F, well now we want it to be equivariant up to homotopy. So we'll add in that F commutes with iota k up to homotopy. Great. Good. Great. And if two knots are concordant, well, then there exists an iota k local map between their knot flow complexes. Great. And now, well, we can define a iota k self-local equivalence. Right, so an iota k self-local equivalence is an iota k local map. Great, and then you can define maximal in the same way. So let's also copy that part of the definition. An iota k self-local equivalence is maximal if for all iota k self-local equivalences, the kernel is contained in the kernel of F. And then, well, the iota k connected complex is just the image of any where F is the image of F is any maximal iota k self-local equivalence. So now let's look at some examples. So look at the same. So if you look at the connect sum of the trefoil with itself, right? So before the CFK connected was just the staircase, but now if you write down what iota does, iota sort of sends mixes the square up with the staircase. So now it turns out that the iota k connected complex is actually this whole thing, exactly because iota sort of sends part of the square to part of the rest of it. Similarly, the figure 8. Again, iota k sends part of the square to this isolated generator. So the iota k connected complex is again the whole thing. If you were to look at the 2 minus 8, so these 2 rectangles in a single generator. Right, so sort of very loosely, I told you that iota k sort of pairs symmetric summand. So iota k sort of sends rectangle to this rectangle and vice versa. And so for the 2, -1 cable of the figure 8, the iota k connect complex is just this single generator here. And that's in contrast to what happens for, say, the 3, -1 cable of the figure 8. So the 3, -1 cable, remember, has these 2 rectangles here. I'll draw the other piece in a different color, maybe so it shows up better. Then it has this sort of, not quite Tetris piece, but this piece here. And then there's this isolated generator. And so what iota k does here is it effectively sort of swaps these 2 rectangles, but then this blue piece here gets sort of intertwined with this generator here. So the iota k connected complex of this consists of this blue piece here together with here. Okay. Are there any questions? All right, so we have the following proposition. Which is that the iota k connected complex for these odd cables of the figure 8, what do they look like? There's sort of a generalization of this picture here. So there's sort of this upside down L-shaped piece. where this length here is n, this length here is n minus 1, and then we have this. Great, yeah. So the iota k connected complex of these odd cables of the figure 8, they look like this. So well, how do we compute that? So this computation relies on, well, the first step is the cabling formula in terms of immersed curves of Hanselm and Watson. So for the experts in the audience, immersed curves, you work over the ring after join UV, but you quotient out by the ideal generated by U times V. But it turns out that in simple examples, well, once you know things over this ring, you can lift it to you can UV by using d squared equals 0. So that's what we do. We need some additional grading information. So for that, we turn to the Ina Petkova's work on cables. So we get some grading data from the work with Petkova. Great. And it turns out that, well, iota k satisfies certain formal properties. So it squares to this Sharkar map and it's skew equivariant map. And so we're able to get a partial computation of iota k just using formal properties. So just knowing that it's a graded skew equivariant map that squares to be this Sharkar map sort of pins down what it has to be up to homotopy for computations. Right. So that's how we compute this connected complex here. And then well, we also have to show that these knots are linearly independent. So remember, there's a Concordance type formula in knot flow homology for connected sums. So the knot flow complex of a connected sum of two knots with images in the involutive setting. Okay, well, this is given by, I'll call it the tensor product of the corresponding iota k complexes. It's a little bit cheating because I haven't told you how to tensor iota k, but the point is just to define. If you define this tensor product in a suitable way, then what I'm writing here is true. Okay, so maybe this tensor product has to be suitably interpreted.
Did you say that you actually know what the Sharkar map is for this complex, or are you saying the formal properties of that map, if you were to know it, sort of imply enough about?
Yeah, we know. If you know the knot flow complex, like the Sharkar map is given by like phi psi. So you know it here. So you know what iota k has to square to up to homotopy, and then the grading properties and the fact that it's a skew equivariant chain map pins down where it is up to homotopy. It's sort of when you look at the calculations, we just sort of got really lucky that sort of like this answer is simple enough that like there just wasn't much stuff that could happen, and any stuff that could happen was actually all the same up to homotopy. Okay, and so then the point is that well, you look at these complexes, and so you look at them under tensor product, and they end up being linearly independent. Basically, the fact that sort of this length here is given by sort of the cabling parameter. That's what gives us linear independence. So they're very roughly the length n differential. So this length n differential is the one right here. Right. So the point is that this sort of persists under the tensor product. And then that's enough to give us linear independence. Okay, so that's a sketch of the proof. And so maybe I'll conclude by just talking about some further questions. Okay, well, it was sort of a paramount that this cabling parameter was odd, right? So if you look at so these two examples here these examples here are sort of like indicative of what happens, right? So the point is, if the cabling parameter is even, you get sort of an even number of boxes that all sort of get paired up by iota type. Whereas if the cabling parameter is odd, there's sort of this like odd shape out, is this one, and that's what gives us a non-trivial iota K connected complex. And so a future question would be, it would be nice to be able to determine whether these even cables are spliced. Note that by work of Miyazaki, these are not ribbon. So the expectation is that these knots are not sliced, but I don't know of any obstructions that work. Great. And also, so we've been talking about rationally spliced knots. And maybe I'll point out that all known examples of rationally spliced knots. Right, so remember rationally spliced knots, so this is the kernel of the map from the concordance group to the CQ. These all bound in Z mod P homology balls, where P is odd. Great. So, i.e., they bound in W with like H1 of W Z mod 2. So in other words, all known examples of rationally spliced knots lie in the kernel of the concordance group to C, CP, or P odd. Right. So here, right. So C sub Q was the concordance group where we look at disks and rational homology balls. So C sub look at things that are sliced in Z mod P homology balls. And so some open questions. Well, is the kernel from the concordance group to C sub Z mod 2? Non-trivial. Or you could look at the kernel from the concordance group to things that are sliced in integer homology balls. Or maybe the real question that everybody wants to answer. The real question is the kernel of the map from the concordance group to, I'll write it C sub H, where this is homotopy. So this is I'll say this is knots in S3 mod, knots that are spliced in homotopy B4s. Great. All right. So that's all I want to say. So I'll stop there.